All right, so today we're looking at trig equations, day 2, and we're just starting to build on the type of equation, right? So yesterday you rearranged, you isolated for your ratio. Today, we're now starting to kind of build on that. So we could have said like yesterday was almost like solving grade 9 equations, right? Now we're starting to solve your grade 10 equations, right? Because what you'll notice is we have a cos squared x, a cos x, and then no coses, right? So we have a descending degree on cos. So cos squared x is just cos x times cos x. And that gets written as our cos squared x, which we know from our previous work. Okay, so we see this descending degree on x. So now we've just started to introduce factoring. But what we're going to get back down to at the very end is still what we were working on yesterday, which if you recall is still what we were working on a week ago, right? So I want you to think about, you can just look at your coefficients, right? We have a 2, we have a 1, and we have a negative 1. So again, I am thinking I'm going to factor. So I want to factor this. There is I cannot common factor, so there's a coefficient of 2 on my leading term. So I know I do not have a simple trinomial. So I'm going to use my fast factoring or guess and check, however you like to call it. So I have 2 minus 1. So I have a 2 cos x minus 1 times a cos x plus 1. And that's going to equal 0. Now I have terms written as they're factored, they're separated by multiplication, it equals 0. So now I can set each of those brackets equaling 0. So again, I'm going to show you this step, but by all means, we do not need to write that out, right? So we're setting each of those equal to 0, which each of those individually just look like what we did yesterday. So now I'm going to isolate for those trig ratios, and at this point, we're now just solving. So we get back down to exactly what we were doing yesterday and last week. So again, cos is positive, where the adjacent side is positive. Drop my height, adjacent over hypotenuse. And I know that's my pi by 3. So therefore, x will equal a pi by 3, or 5 pi by 3. And in this case, where's x equal, cos of x equaling a negative 1? Well, maybe I can think about where's my adjacent side negative. So maybe I'm thinking this, where's my adjacent side in the negative? It exists at pi. Or maybe because we're so good now with our cos curves, we do a quick sketch to go where is cos at a value of negative 1? Well, that is when x is equal to pi. So again, you'll notice all we've done is added a step to this, but it's a step that you are used to doing. You guys know how to factor. So let's continue to work on that. Okay, so now I want you to take a moment and think about what's happening in B. So in B, I'm hoping you notice we have a sine x, but we also have a cos squared x. So in our first example, everything was written in terms of cos. In this next example, we notice we have a sine x and a cos squared x. So I want you to think about what strategy could you use in order to write them in terms of the same trig ratio. So we know, if you recall, we know that sine squared x plus cos squared x is equal to 1. So if I were to rearrange that, I know that cos squared x is equal to 1 minus sine squared x. I have no trig identity just for a sine x, right? There's nothing that I have there that's going to allow me to work with that. So instead, I recognize I have a cos squared x. I can change that. I can replace it with a 1 minus sine squared x. And now everything that I have will be written in the same trig ratio. So at this point, we're just going to expand, and I'm going to move everything over to one side. At this point, we're going to look to factor and use our quadratic formula. Or sorry, factor or use quadratic formula if we cannot factor, right? So now you'll notice we have it written in terms of sine squared x, sine x, no sines. So we have a descending degree on sine x. Okay, so I've had some time to factor this. I need a negative 12, so my numbers add up to a negative 12, so I have my 2 sine x minus 1 times 2 sine x minus 5 is equal to 0. Therefore, sine x equals a half, or therefore sine x equals 5 halves. So again, for what values of x, so for what angles on our sine curve, or for what angles when we think about the ratio of opposite to hypotenuse, give us a ratio of 1/2. So again, we know sine is positive in quadrants 1 and 2. Opposite over hypotenuse, we know that's our pi by 6. So therefore, x is equal to pi by 6, or 5 pi by 6. Now I'm going to draw for you just our curve for a moment to think about our sine curve. And so again, this is asking us for what values of x, so for what angle on our sine curve do we have a ratio of 5 halves? So for what angle do we have a y value of 5 halves? And if we think about what 5 halves is, right? So when you think about that, where do we have a y value of 2.5? We don't. There is no y value on our sine curve. There's no angle that gives us a y value of 5 halves. So our answer for this one would be no solution. So we are unable to have an angle when we have a y value of 5 halves. Please be careful though. That would be the case for our sine and our cos curves. But for tan, for secant, cosecant, cotangent, those would have values that are greater than 1, right? So just be mindful of that it depends on what trig ratio you are working with, right? In this case, sine does not have a y value that's greater than 1 or less than negative 1, okay? But please be mindful of that depending on what your trig ratio is that you are working with. So take a minute from start to finish. Let's work through question C. So now I've made some adjustments in D for you. You'll notice I've given you sine x times cos x equals sine x. So you'll notice we do not have a sine squared x or a cos squared x, so I cannot replace those using my trig identity of sine squared x plus cos squared x equals 1. So I want you to think about what other tools do you have and other resources of how you could go about answering this question. So when we look at this question, our first thought for most of us might be to divide both sides by sine x. Now, I'm going to caution you away from that, and I'm going to take you back to something that you're aware of to help you see it in terms of sine and cos, okay? So if I had given you x squared equals 3x, and you had divided both sides by x, you would have gotten that the answer to that is x is equal to 3. However, we know that if we were to move that 3x over and common factor out an x, that the answers, the possibilities here, are actually that x can equal 0 or 3. So by dividing our sine x out of each side, we are actually dividing out possible solutions. Okay, so we don't want to divide both sides by a sine x, or in this case, our x. Rather, we want to look to common factor. Okay, but very common thought process. So I'm going to just make a note here that we want to ensure that we common factor. Okay, so I'm going to bring the sine x to the other side, and now I can common factor out a sine x out of each of those terms to ensure that I have not eliminated any of my solutions. And now we're just back to what we were dealing with. Here, sine x equaling 0. So again, you can think of your unit circle, or my guess is at this point for us, drawing our curves might actually be a bit faster for us. So where is sine x equals 0? So for what angles? Well, that's going to be at 0 or pi or 2 pi. Where does cos x equal 1? It equals 1 at 0 or 2 pi. So I'm hoping what you'll notice is if we had divided out our sine x and had only left it as cos x equals 1, we would have had the values of x being 0 or 2 pi, when really we also have the answer of pi would work. If we subbed in pi for x, our left side would in fact equal our right side. So what I would suggest doing after we write this is we don't need to leave all of these statements as separate statements. We could just write one final statement that includes any overlap between those two answers. So in question 2, we're still solving for x. So we're still finding the values of x that make these equations true. However, I'm hoping you'll notice I have removed any type of domain restriction here. So if you look back to question 1 that you wrote down, I said solve for x, and I said solve, between x is between 0 and 2 pi. What you'll notice here, I've removed that restriction now. So what that means for these answers, we are now also going to state general statements for it. So we're going to get our final values for x, and then we're going to look at the values that we have and write general statements for them. So before we get to that point, we are going to approach this in the exact same way that we have approached our other questions. I notice that I have a sine squared x, a sine x, and then no sine x's, so I have a descending degree on my sine, which means I'm going to look to factor. If I cannot factor, then I am going to look to use quadratic formula. So because we've done a bunch of these already today, let's look to just factor. Okay, so a couple things happening here. So this now is our first example. So you might be asking, okay, so why did I give you this example? Well, I've removed the restriction of 0 to 2 pi. And you'll notice I've now also given you one of your ratios that we do not have a special triangle for, right? So we notice that 2/3 are opposite side to our hypotenuse. We do not have a relationship of the opposite side of being 2 and our hypotenuse being 3. So again, sine is negative. So I know sine is negative where its opposite side is negative. So that tells me what quadrants I'm in. I am going to use my related acute angle and now use the positive ratio for sine. and I find out that that's going to be approximately 0.73. And so now I recall that that is my related acute angle, so that is what I have in here. So for my values of x, I am going to have pi plus 0.73, which will give me approximately 3.87. And I'm going to have 2 pi minus 0.73, which will approximately give me 5.55 radians. And then we know when on our sine curve where to sine, for what values of x is sine at a y value of 1. Easiest way is to just look at my sine curve, and I know that that occurs at pi by 2. So that would have been a fantastic answer if I was asking between 0 and 2 pi. However, so now we know that x is equal to 3.87 plus 2 pi k. K is an element of integers. X is equal to 5.55 plus 2 pi k. I wrote two statements because I know these do not repeat at regular intervals. I could tell that by sketching myself a curve. Or I can tell that the distance between the terminal arms is not equidistant. So therefore, I'm going to need two statements in order to rotate back to each of those terminal arms. And lastly, I know that I reach a y value of 1 on my sine curve. That is going to occur every 2 pi. So I will have pi by 2 plus 2 by k, where k has to be an element of integers. And so that last piece that I have there in red is how now we would transition from having the restriction for our domain from 0 to 2 pi to just being asked to solve for x. So in B, I notice I have a cos squared x, a cos x, no cosis, so I have a descending degree on cos. I'm looking to factor. I notice that I cannot factor. So I'm going to use quadratic formula. So I want to make sure that we get set up with our quadratic formula correctly, and then I'm going to give you a minute or two to try it. Okay, so you may be tempted just to write x is equal to, because that's what we do when we have quadratic formula. But this needs to be written as cos x, right? This is no longer just your x squared minus 5x minus 4 equals to 0. It's a cos squared x minus a 5 cos x minus 4. So for our quadratic formula, we set that equal to cos x equals, and then we can go through. Just as we would normally for our quadratic formula. Okay. So if you feel like you're confident with this, take a minute or two and work through and see if you can get to your final answer. If you're not feeling so confident with it, I'm going to take it through with you. So if you are feeling good, just tune me out as I go through this and see how you do from start to finish. Okay, so what we notice is I have two answers here, right? I have a 5 plus root 41 over 2 and a 5 minus root 41 over 2. I'm hoping we go, okay, square root of 41 is going to be 6 and a bit. So 5 plus 6 and a bit is 11 and a bit divided by 2. I'm going to have 5 and a bit happening here. So that one answer is cos of x equals 5 and a bit, which I'm hoping we're going, okay, there is no value of x, there's no angle on my cos curve that has a y value of 5 and a bit. The value is greater than 1, so we do not have this answer. So I am going to state that as inadmissible. Now I want to quickly just tell you the difference here. You might be going, wait, why did we write that as inadmissible when last time we wrote it as no solution? Fantastic question. I can write it as inadmissible here because I've included the plus and minus in my solution. It is not, really it's not considered a complete equation, okay, because there's a plus and minus there. So if I had written it out this way and said cos x equals 5 plus square root of 41 divided by 2, or cos x equals 5 minus the square root of 1 over 40, the square root of 41 divided by 2. If I had written them out separately, now I would be writing here that this is no solution because it has been written on its own, and that is a ratio that we have stated. Okay, so that's just the difference there, if you're wondering why all of a sudden that changed. Okay, so let me just clean that up. So then we can look at our other option, 5 minus 6 and a bit divided by 2. Well, we go, okay, that fits within 1 and negative 1. Okay, so let's just work now with cos x equals 5 minus the square root of 41 over 2. And again, I said 5 minus 6 and a bit divided by 2. So we know we're going to have a negative value. So negative value for cos tells me my adjacent side is, in fact, negative. Okay. So at this point, I'm going to say that I'm okay if you guys use your calculator at this point. Okay, so if you type in here cos x and you type in 5 minus the square root of 41 divided by 2, you're going to get that it's approximately negative 0.70. So one thing you need to be really careful about, that's my ratio. So that's the same as when we had cos x equals a negative 1 over root 2. Cos x equals negative 1/2, right, where we used our special triangles. This is still our ratio. This is not my related acute angle. That is just my ratio. So I have cos is negative. So that's why I put my terminal arms in quadrants 2 and 3. I still need to find my related acute angle. So I have cos of alpha. I need to use the positive value for that. Type it into my calculator, and I get my related acute angle is approximately 0.79. So that now is my related acute angle. I'm sounding so strongly about that because this tends to be the most common mistake when we deal with quadratic formula or when we deal with this ratio being a negative, is we start to assume that that's our related acute angle, and it is not. Okay, we still need to find our related acute angle. Now, once I have my related acute angle, I can find those actual values of x. And what I'm hoping we'll notice, because we have to write general statements, these terminal arms are not equidistant from each other. So I know I'm going to have to write two statements. So at this point, let's do this all at the same time. So I have x is equal to pi minus 0.79, which means that that is going to be x is equal to around 2.34 approximately, plus 2 pi k, because I know it's going to happen every 2 pi units. And then I know that x is equal to pi plus 0.79. So 3.93 plus 2 pi k. K is an element of integers. So, a couple things which I think we should be pretty proud of, right? We just used quadratic formula for a trig equation. That quadratic formula gave us obviously an approximate, and it was negative, our ratio, so we used that negative to then find our related acute angle, and then we use that information to interpret where these values for x actually occur. So a lot happening here, lot to wrap your mind around, but also a lot to be proud of if you're kind of mapping that through and being like, okay, I can see where that's coming from. So when we look at C, again, we're noticing, okay, I have two terms happening here, right? Tan x times cos squared x is one term equaling tan x. We don't want to divide both sides by tan x because we're eliminating that possible solution. So again, we have a case where let's bring everything over to one side and let's common factor. So that alone, we know, okay, well, Ms. Katie's already given us a question like this, so where are we going? So what you'll notice, I'm hoping you'll notice, is that there's still this squared here. And so now we've common factored, but we also now have this cos squared x minus 1. So let's deal with the tan. So we know that therefore tan x equals 0. So you're also probably going, okay, this is the first time she's put tan into our question. And we know that cos squared x minus 1 is equal to 0. So let's deal with the cos squared x first because we've been dealing with cos already in this lesson. So I've written it this way instead of just making it cos squared x equaling 1 for a reason. Some of you are going to look at that and go, okay, well, I can factor that. And then you're going to go and solve it from there. What I would encourage you to do exactly what you would have done back in grade 10 when you would have been taught, okay, how many terms have a variable in it? Just one, right? So if you had been given x squared minus 9 and you were asked to solve, I'm hoping you're going, okay, I have one term with a variable, so I can isolate. Once I isolate, I can square root both sides, and I'm left with a plus or minus answer. Same thing here. We have one term with a variable, so let's isolate, which I could have done from step 1, right? Like I could have gone straight to here from that initial step, square root both sides, and now I just have the square root of cos squared x is cos x, so I'm going to have cos x equaling a plus or minus 1. So when I think about my cos curve, we're at a 1, we're at a minus 1, and we're back at a 1. So the values that work for x are 0, pi, and 2 pi. All right, we'll deal with our general statement for that in a moment. Now let's go back over to tan. Where is tan x equaling 0? So again, you can think of your unit circle. So where is my opposite side 0? Or maybe you've become very familiar with your tan curve and you just want to draw yourself a quick sketch. Maybe you're going tan is sine over cos. So if I think about where sine equal to 0, then I know where tan is equal to 0, right? So a number of different ways, again, we can be thinking about that. So we know that that's going to be at 0, pi, and 2 pi. So a few things to note here. My answer for tan x equaling 0 are x is equal to 0, pi, and 2 pi. My solution for cos x equaling plus or minus 1 is x is equal to 0, pi, or 2 pi. So we can simplify all of this to one statement that x is equal to pi k. You'll notice it's going to occur at one of these answers every pi units. And instead of me starting at 0 and saying plus pi k later, I can just simplify that and write x is equal to pi k. So let me just catch up to where you are. So you've brought this over. We've common factored out our cos x. Set each of our factors equal to 0. I can think about my cos curve if that's easier. Where is cos at for what angles is cos at a y value of 0? It is at pi by 2 and 3 pi by 2. For tan, when is tan at a value of 1? So maybe your curve helps, maybe you're going tan is positive in these quadrants, opposite over adjacent, means that I'm dealing with a pi by 4 angle. So therefore tan is at 1 at our pi by 4 and 5 pi by 4. And then you go, okay, well, I know these ones occur every equidistant from each other. So I can write one statement there. These terminal arms are equidistant from each other, so I can write one statement there. Great, and I'm done. I want to have you pause for a second, and I want you to look at those answers. Now I want you to think about your tan curve. What does tan have that sine and cos do not have? Tan has asymptotes. I want you to think about, where do the asymptotes on our tan curve occur? So if you think about tan, where do those asymptotes occur? They occur at pi by 2 and 3 pi by 2. So I want you to think about that. If x is equal to pi by 2, and I have to sub pi by 2 in for my x's if I were to check left side, right side, that would give me undefined times cos of pi by 2 equals cos of pi by 2. I'm hoping we can really see the problem that occurs there. So when we think about these answers that we've just calculated, we cannot use x equals pi by 2 and 3 pi by 2. Those answers are in fact inadmissible. And the reason for it, because tan of x is undefined, it has asymptotes at pi by 2 and 3 pi by 2. Another way you can maybe think about that is we know tan x is equal to sine x over cos x. So if cos x equals 0, then we know that this fraction is actually undefined, right? We cannot have 0 in our denominators. So our only solution to this question would be that x is equal to pi by 4. When does that occur? It occurs every pi k. So again, you'll recall the period of tan is only pi. So for a question like this, do you have to state for me all of your restrictions? No, absolutely not. But we do have to be mindful of when our question has a tan of x in it, a secant x, a cosecant x, a cotangent x. Any trig ratio where there are reciprocals that have, or any trig ratio rather, that has an asymptote, we have to be mindful that do our values of x exist where those asymptotes exist, right? Because if a value of x that we get also occurs at the asymptote for one of those ratios, we cannot use it in our answer, okay? So that's why you'll notice when we were just working with sine and coses, we did not have to take into account asymptotes at all. But as soon as I introduce tan of x, we have to be mindful of our solutions and just do a quick double check to make sure that none of those solutions occur at an asymptote. So those are the examples that I have for you. There are practice questions posted.